Magnetism is a very important topic, and we find magnetism in our daily lives every day. It's all around us. Computer storage, mainly hard disks, are magnetic storage. We have toys that have magnets in them. Doorbells have magnets. An electric motor, a generator, elevators, all of these have magnets. Our Earth is a magnet. So the Earth has its own magnetic field. As you can see in this diagram, the magnetic poles do not coincide with the geographic poles. So the line joining the magnetic poles is not the same as the line joining the geographic poles. That's the first thing. Another thing is that if you look carefully, you can see that the Earth's south pole is wrongly named the North Pole. So that's a point of confusion. So the Earth's south pole is actually called the North Pole. But it really doesn't matter because we know that the magnetic poles of the Earth flip once every so many years. We can't say how many years, but it flips. The north becomes the south and the south becomes the north. So, but it's important to know that the Earth has a magnetic field. And that is why if you take a bar magnet and freely suspend it in the Earth's magnetic field, the bar magnet will always point north-south. That is the principle of a compass. But remember, it's not pointing along the geographic north and south, but it's pointing along the magnetic north and south. That is just a little bit off from the geographic poles. Okay, now as I said, remember, the Earth's magnetic field flips after long time intervals. So it really doesn't matter how we name them, okay? And you can also see the Earth's magnetic field shown here. Magnetic lines always start from the North Pole and go to the South Pole. And then they do not stop at the South Pole. Instead, they continue through and loop back to the North. So the magnetic lines are closed. Magnetic field lines are closed. Remember that electric field lines are open. They start on a positive charge and end on a negative charge. But when you come to a magnetic field, the lines start from a North Pole, go to the South Pole, and through the magnet loop back. Whenever a charged particle enters a magnetic field, there will be a force acting on it. And the direction of the force depends on the direction of the velocity and the direction of the magnetic field. So here we have three vectors. The velocity of the charged particle, the magnetic field, and the force. These are the three vectors. And the direction can be found out using what's called the right-hand rule, in which the right hand palm is used in such a way that the fingers first point in the direction of the velocity of a positively charged particle. Remember, we're talking about a positively charged particle, and the direction of its velocity is given by the fingers towards the tip. And then when you bend the fingers at right angles, that now shows the direction of the magnetic field. So, number one, it's a positively charged particle moving that way, as shown by the fingers, and then you bend it at right angles, that gives the direction of the magnetic field. If so, the direction of the force is given by the thumb. So that's the right-hand rule, and it's shown here. The fingers show the direction of the velocity when it's stretched, and then you bend it right angles to show the direction of the magnetic field, and the force is given by the thumb. Remember that if it's a negative charge particle, then we will have to hold the fingers opposite to the direction in which it is moving. Which means if the negative particle is coming towards me, then the fingers have to be held in the opposite direction like that. Okay, so remember that it's a little different for a negative particle. So that gives the direction. But the magnitude of the force acting is given by F is equal to Q V cross B. Q is the charge of the particle, V is the velocity, and B is the strength of the magnetic field. And a cross product is usually written as sine theta. So V cross B is VB sine theta, where theta is the angle between the velocity and the magnetic field. So as in this case, if the angle is 90 degrees, as in this case, then sine 90 becomes 1 and the force becomes maximum. So maximum force acts on a charged particle when it is moving at right angles to a magnetic field. Okay? And this actually helps us to find the unit of magnetic field. Remember, in the International System of Units, the unit of magnetic field is represented by the units of current, because the base unit is ampere. So now I'm going to show you how to get the unit of magnetic field. First of all, I've rearranged this equation to make B the subject. Then substitute the units for each quantity. F is force in newtons. Q is charge. And remember, charge is current multiplied by time. So I'm going to do that. And then velocity is meter per second. So there you have it. So you see the second and the second will cancel out and you get Newton by ampere meter, which is called Tesla. So the strength of a magnetic field is represented by Tesla. But there's also another unit, as you can see, Gauss. 1 Gauss is 10 to the negative 4 Tesla. 1 Gauss is 10 to the negative 4 Tesla. All right? So remember that. The direction of the force is given by the right-hand rule. Remember, it's a little different for a positive and a negative charge. And then the unit of magnetic field is Tesla. Let us now work out a problem using this formula. So an electron moves with velocity V is equal to 7.0 I minus 6.0 J times 10 to the 4 meter per second. In a magnetic field B, negative 0.80 I plus 0.60 J Tesla. Determine the magnitude and direction of the force on the electron. So we're given the two vectors, which is the velocity and magnetic field, and we are asked to calculate the force. We know that force is given by Q V cross B. Since we have to find the cross product, we're going to represent the vectors, velocity and magnetic field, using matrices. So you have Q, which is the charge of the electron, negative 1.60 times 10 to the negative 19. And then you have IJK. You see that I is 7.0, I is 7.0 for velocity, and then you have J as negative 6.0. For the magnetic field, we have negative 0.80 and 0.60. So it's V cross B. So first we put the coefficients of velocity, then followed by that of the magnetic field. And as for the k vector, there are no coefficients. There's no k for both the vectors. That's why both are 0. And then to take the cross product, this is what we do. To find the coefficient of I, you go look at the j value. This multiplied by 0 minus 0 multiplied by 0.6. So we go from right to left, take the product, minus this way, again take the product. In this case, both of those will be 0. Because when you multiply this with 0, you get 0. This multiplied with this is also 0. So I will have no coefficient. Well, when it comes to j, now you take this coefficient multiplied by 0, which is again 0, minus this multiplied by this, which is again 0. So j will have no coefficient either. Excuse me. But when it comes to k, you have to take the product of this times this minus this times this. So I'm going to write that. So first of all, that is the charge of the electron, and here 7.0 times 10 to the 4 minus 0.60 minus this times this, as I'm clearly showing you. Be careful with the signs. You know, when you take that product, of course that's the charge of the electron, and then when you take the product here and take the difference, this is what you get. You get negative 0.6 times 10 to the 4 k. So now you multiply these two, and that will give 9.6 times 10 to the negative 16 Newton. That gives you the magnitude and the direction of the force. How do you know that you get the direction? Shows that the direction is along k, means along the z-axis. And here is the magnitude of the force. So that's how we calculate the cross product. Here is another example, slightly different, but using the same idea. An electron experiences a force F is equal to 3.8 I minus 2.7 J times 10 to the negative 13 Newton when passing through a magnetic field B is equal to 0.85 Tesla K. Determine the electron's velocity. Now the difference in this case is that the force is given and so is the magnetic field, and we have to find the velocity. So the idea is the same. Excuse me. F is Q, V cross B, and that's Fxi plus Fyj, because the force is going to have two components. It's given here. It's only I and j, so I've written it as Fxi plus Fyj, which is, as we did before, represented in matrix form. Negative E is the charge of the electron, and then you have Vx, Vy, Vz, and of course Ijk. And here are the coefficients. So in this case, I've not written Ijk on top, but it'll be easier if you write that on top. Okay, that's it's going to be negative E Vy Bz. Vy Bz. I'm going to explain that. Minus E negative Vx Bcj. So that's what you get. Why? Because when you want to find it out, okay, let's take this a little. Okay. When you try to find it, what you do is to find I, you go Vy Bz, correct? Minus Vc0, which is 0. So I've not written that. So the coefficient of I would be here, would be Vy Bc minus 0. That's why you have minus E Vy Bz I. Now to find that of J, you go Vx Bz, right? Vxbc, but for J, remember, you have to put minus. For J alone, remember, it's a negative, so that's why you get negative Vxbcj. Okay? You change the sign for the J. You put a negative there, negative J, so you put negative J Vxbc minus Vc0, which is again 0, so it's negative J Vxbc, and then you have got a negative outside. So that's why you have two negatives here. Okay, so that's how you set it up. And then as we continue, we put the coefficients of like terms equal to each other. The coefficient of I here is fx, and the coefficient of I here is this whole thing. So that's why I'm going to put fx is equal to negative e vy bz. And that will give us the value of vy as negative fx by ebz. And now I can substitute the values because fx is given as 3.8 times 10 to the negative 13. E is the charge of the electron. Bz is given as 0.85. So when I substitute those, charge of the electron and Bz, which is 0.85, that is calculated as negative 2.8 times 10 to the 6 meter per second. Okay, so we get the value of fx. Now similarly, we can find the value of fy by putting the coefficients of j equal to each other. For j on this side, we have fy, so we're going to put fy is equal to, the coefficient of j here is this whole thing. Okay, and two negatives make a positive, so keep that in mind. Fy is EVxBc. So the two negatives became a positive. Rearrange that and you get Vx as Fy by EBz. And Fy is 2.7 there. And then you have the charge of the electron and again 0.85. So put those numbers in and calculate. We get it as negative 2.0 times 10 to the 6 meter per second. Which means now we have the velocity as negative 2.0 I plus 2.8 J times 10 to the 6. Oh, I'll have to write that again because it's hidden. So the velocity of the electron is negative 2.0 I plus 2.8 J times 10 to the 6 meter per second. Just a few points about magnetic field lines before we transition to the next topic. I've already mentioned that magnetic field lines go from north to south, and then inside the magnet they continue from south to north. So magnetic field lines are closed. And this is the representation of the magnetic field due to a bar magnet. Oh my goodness, sorry. Due to a bar magnet. Here you have the magnetic field due to two opposite poles kept close to each other, and you can see that the magnetic field goes from the north to the south, right? And here you have two like poles, so you have a north and a north, so the field lines repel. Okay, while in this case they attract, while here they repel. And then a few points about the magnetic lines itself. Remember, strength of a field is proportional to the density of the lines. So if you take this part, the lines are closer, that means the field is stronger as compared to this part where the lines are not that close. So if the magnetic lines are closer, that means if their density is higher, then it's a stronger magnetic field. And that's how we represent it. So that's number one. And two, magnetic field lines are always closed. Number three, it's from the north to the south outside the magnet, but inside it's from south to north, as you can see. Outside it's from north to south, but inside it's from south to north. Field direction at any point is along the tangent drawn to the line at that point. As an example, if you want to find the magnetic field direction at this point, draw a tangent to that magnetic field line. Remember, that's the magnetic field line. You draw a tangent at that point, and that gives the direction of the magnetic field. But that's at point P. If you want to find the magnetic field direction at Q, do the same thing. Draw a tangent at Q. So you can see that the magnetic field direction is changing. And it's given by the direction of the tangent drawn to the line passing through that point. Can two lines intersect? Never. Two field lines can never intersect, because if they do, then there would be two directions, because you can draw two tangents at that same point. Then that would mean that the magnetic field is along two different directions at the same point, which is impossible. So magnetic field lines do not intersect. Magnetic field lines do not intersect. So those are the important points about magnetic field lines. Cut. Here's an important scenario. You know, if you look at this diagram, you see tiny blue crosses, which represents the back part of an arrow, which means that the magnetic field is perpendicular to the screen and into it. So crosses show a magnetic field into the paper, while dots, if they were dots, they would show the tip of the arrow. That would mean the magnetic field was coming out of the paper. Okay? So crosses show a magnetic field into the paper, perpendicular to it, and dots would show a magnetic field out of the paper, again perpendicular to the paper or the screen. So in this case, the magnetic field is into the screen. And then you have a charged particle. Let's assume it's actually shown to be a negatively charged particle. It's a negative charged particle moving in this direction. You know, it's moving along this direction. So it's entering the magnetic field at some point along this direction, okay? But as soon as it enters, a force begins to act on it. Can we find the direction of the force? Yes, remember the right-hand rule. Okay, let's check it out. It's a negative particle, and it's moving in the plane of the paper, right? In the plane of the paper, that way. So because it's negative, we have to hold the fingers opposite to its motion. So the fingers are now, pointing towards me. And then the magnetic field, when you bend your fingers, the magnetic field should be the direction shown. So I have to hold it this way. And since the magnetic field is into the plane of the paper, see that? So if I hold it correctly, I'm going to see that the force acting on it will be in this way, as you can see. The force on the particle is in to the path as shown. It's so tough to show it 3D, but you'll have to use your fingers and try to understand how the direction of the force is. It's a negative particle. Let me try to show it here. It's a negative particle going that way, right? That's easier to show. So I have to hold the fingers in that direction because the negative particle is going this way. I have to hold the fingers opposite. And then when I bend it at right angles, it should show the direction of the magnetic field. And the magnetic field is into the plane of the screen. So you see that? That's a magnetic field. This is how the negative particle is going. So that's why I'm holding it opposite. And see that the thumb is pointing down. Okay. See that? So because of that force, this negative particle, which meant to go straight, which it wanted to go straight across, will not. Because of the force acting downwards, it'll curve down. And as it curves down, the force also curves. See, the force also changes direction, which means if the magnetic field is big enough, in a big area, then the particle will be compelled to move in a circular path. I hope that's clear. And remember, whenever anything moves in a circular path, there is a centripetal force acting on it. So in you know that the formula for the centripetal force is mass times velocity squared by radius. And in this case, that is given by QVB sine theta. Correct. But theta is 90 because theta is the angle between velocity and the magnetic field is 90. So the centripetal force in this case, it will be QVB because it's max and theta is 90, remember? So we're going to write QVB is equal to mv squared by r, centripetal force. Rearrange that and you get the formula for radius of the path. So the radius of the path taken by that charged particle depends on its mass, depends on its charge, depends on its velocity, and depends on the strength of the magnetic field. So which again means that if the magnetic field is really strong, the radius is going to be small. So it'll be compelled to make a smaller circle. If the magnetic field is weak, it may not even make a circle. It might just curve and go out of the magnetic field. Okay? Right, so that's the formula for radius of the path taken by this charged particle. And we can also find the time period. Remember, time period is the time taken to make one full circle. And that is simply the circumference, 2 pi r, divided by velocity. Because time is distance by velocity, 2 pi r by velocity. And since we know what r is, we can substitute the value of r from there. So 2 pi by velocity times the radius is mv by qb. The velocities get cancelled. And you get 2 pi m by qb. Very interesting that the time period does not depend on the velocity because the velocity got cancelled out. That's very interesting, which means no matter whether the particle is moving slow or fast, it's always going to make the same time to move around in a circular path. The reason being that if it's moving fast, then the radius is going to be bigger. So it'll compensate. It's moving fast, makes a bigger circle. If it's moving slow, it makes a smaller circle. So the time in both cases becomes the same. And the time depends only on the mass and the charge of the particle. Well, in the previous case, we considered that the particle was moving at right angles to the magnetic field, remember? What if the particle is not moving at right angles? What if the particle has a velocity which is not at right angles? Then we will have to resolve the velocity into two components, into the perpendicular component here and the parallel component, parallel to the magnetic field and perpendicular to the magnetic field. Now what will happen is the perpendicular component rather will determine the radius of the circle that the particle makes. But since it has a parallel component, it will not be just making that circle right in that same place. It will also be moving forward. That's why you get a helix. So you see, it's making a circular path, but at the same time, because of the parallel component, it's also moving forward in the direction of the magnetic field, as you can see. So it's making a helical path. So that's a helix. And we can find the pitch of the helix. The pitch of the helix is the distance between consecutive circles or circular paths. You know how much it moves from one circle to the other. We can find that. But first of all, the perpendicular component is going to be v sine theta, and the parallel is v cosine theta, where theta is the angle made by the velocity with the magnetic field. Remember, that's the theta. Okay? And so the pitch of the helix is given by time period multiplied by the parallel component. And we know that time period is 2 pi m by qb from the previous discussion. So the pitch of the helix is going to be given by parallel component into pitch. And I'm going to show that with a simple problem here, which will rather explain what I've been trying to give you. So here is an electron which enters a uniform magnetic field. Let's move that fast. Enters a uniform magnetic field of 0.28 Tesla at a 45-degree angle to B. So theta is 45 degrees. We have to find the radius and the pitch of the helix. Okay? Now the radius is determined using the perpendicular component, and the pitch is determined by multiplying the parallel component with the time period. Now, in this problem, we have to see, it's given that the speed is 3 times 10 to the 6 meter per second. So it's moving really fast. Okay? So let's first find that's the diagram. That's the radius, which we could find. Radius is given by mass times perpendicular velocity divided by qb. Mass of the electron will be given. That's the mass of the electron, 9.11 times 10 to the negative 31 times the perpendicular component is the velocity multiplied by sine of the angle divided by the charge of the electron multiplied by the magnetic field, which is 0.28. So when we do all those calculations, you get 4.3 times 10 to the negative 5 meter as the radius. Next, we find the time period using 2 pi m by qb. Once you get that, just find the pitch by using that's supposed to be the parallel component, and that's why it's a cosine 45. So velocity cosine 45 is the parallel component, times 2 pi mass of the electron divided by qb. Remember, I'm putting in the charge of the electron times 0.28. Okay, when you do that, you get 2.7 times 10 to the negative 4 meter as the pitch. So remember that in the helix, you got to always remember to resolve the velocity into the perpendicular component, which you use to calculate the time period and the radius, and then use the parallel component of the velocity to calculate the pitch. Got it. Now we will look at the force acting on a current carrying conductor placed in a magnetic field. So you already have a magnetic field, and in that magnetic field you take a conductor that's carrying current and keep it there. It's going to experience a force. Now the reason is a current is nothing but flow of charges. We already know that when charges move through a magnetic field, a force acts on it. So now you have a bunch of charges moving through a conductor, which is a current, and so there must be a force acting on it. And the force is given by the charge multiplied by the cross product of velocity and magnetic field. So here it's important to remember that N is the number of charges in 1 meter cube, number of free charges in 1 meter cube. So if A is the area of cross section of the conductor and DL is the length, you know that the volume is A times DL. So when you multiply NADL, you get the total number of free charges in that volume. Because N is the number of free charges in 1 meter cube, and the total volume is A times DL. So when you take the product NADL, and then you multiply it with E, you get the total charge. Because remember, E is the charge of one electron. So NaDl gives the total number of electrons. And then when you multiply that with the charge of an electron, you get the total movable charge. So that's your Q right there. All of this is your Q. And we know the force is Q V cross B, right? And remember that velocity is the drift velocity. So it's Vd cross B. And then we get that force. Remember that the force is dF because we're considering a small part of the conductor whose length is dl. So now we can rearrange this and write it as NEA Vd dl cross B. And remember that NEA Vd is nothing but I in a previous chapter. So that gives us dF is I dl cross B. So you take the cross product between the length and the magnetic field. So in short, or in summary, the force on a current carrying conductor is given by I L cross B. I L cross B. Let me illustrate that with a problem. Okay, so here is a problem there. Suppose a straight 1 millimeter diameter copper wire could float horizontally in air. Oh, this is an imagination. You imagine that 1 millimeter diameter copper wire just floats horizontally in the air. That means its weight is being balanced by an upward force acting on it. Because it's suspended in the Earth's magnetic field and it's carrying current. We just saw that a current carrying conductor has a force acting on it, right? And so this force is upwards and balances the gravitational force downwards. And the Earth's magnetic field is given as 5 times 10 to the negative 5 Tesla. And what current would the wire carry? Does the answer seem feasible? We'll get to that. So here is the conductor with the two forces acting. Mg is the weight acting down. ILB is the force due to the Earth's magnetic field acting up. They must be equal to each other, right? But mass, the mass of the conductor is volume times density. Okay? And what's the volume of the conductor? It's a cylinder. So the volume is pi r squared times the length. Area of cross section is pi r squared times the length gives the volume. So density times volume gives the mass. You see that? And then G. So now the length on both sides cancels out and we can make I the subject and we get I is rho pi r squared G by B. Density of copper will be given, it's 8.9 times 10 to the 3. Pi times the radius is in millimeters. Oh, that's diameter. So, I have to divide that by 2. Okay, and that's the magnetic field there. So that means I had to, because I did not divide by 2, I would have to multiply this with 4, which I did, and that's when I get the answer as 1400 ampere. Okay, because it's the diameter, I had to take the radius, and because it's squared, instead of dividing it by 2, I divided it by 4. And so we get 1400 ampere. Oh, that's a huge current. And so does the answer seem feasible? Never, because such a high current would produce a lot of heat in it. Remember, the heat produced is dependent on the square of the current and possibly melt this conductor. So that's not feasible. That's why we do not see conductors floating in air because of the Earth's magnetic field. So here we have the diagram of a motor. We will discuss the working of the motor in detail in the next chapter. But for now, we just need to look at this coil, this rectangular coil that is carrying a current. As you can see, the current flows down, because it's connected to a battery there. The current flows this way, down, up through this, back here, and into the negative. Current flows from positive to negative. And here you have two poles, magnetic poles, north and south. We know that the magnetic field is from the north to the south. And so when you look at this part, the current is in the same direction as the magnetic field. And therefore, the angle is zero and no force acts on it. But when you look at this part or this part, the current is flowing that way, the magnetic field is perpendicular to it, so maximum force acts on it, right? And the force on this side will be acting down, while the force on this side will be acting up, given by the right-hand rule, okay? Since the two forces are equal and opposite, a torque acts on the coil. And this torque, in this case, counterclockwise, tends to rotate it. So we're trying to find the formula for the torque. So we'll start with the force. Force is ILB sine theta. And I told you that theta is 90 degrees. So it's ILB. And torque. Torque is nothing but the force multiplied by the distance between the forces. Technically, it's the cross product of R and F. In this case, R is the distance between the two, which would be the width of the coil. You see, the width of the coil is represented by the little b. So, R is represented by b, is the distance between the two forces, and the force is ILB sine theta, and now we know that B times L, length times width, gives the area of a rectangle. So that's the area of the coil. So you have IAB sine theta. All right? And there is a new quantity that's defined. But before we get to that, if there are n turns in this coil, that's just a loop. But suppose we had a large number of turns in this coil, then the total torque would be this multiplied by the number of turns. So I'm using capital N to represent the total number of turns. So then the total torque would become, let me write that would become NIAB. Now remember, sine theta has become 1 because theta is 90. And then we have this mu defined as I times A. All right, the little n is a unit vector. I times A is called the magnetic moment of the coil. Magnetic moment of the coil. It's actually I times A, but if it's n turns, then it's NIA. NIA. And so we can now represent the torque as the cross product of mu and B, because you have mu here, NIA, and you have B. So torque is the cross product of mu, which is the magnetic moment, and the magnetic field. So here is a problem to demonstrate the theory that we just looked at. Calculate the magnetic field strength needed on a 200-turn square loop, 20 centimeter on a side, to create a maximum torque of 300 Newton meter if the loop is carrying 25 ampere. Okay, so we have to calculate caps B, the magnetic field strength. The number of turns is 200. It's a square, so the length and the width are both 20 centimeters. And the current, 25 ampere. The torque is 300 Newton meter. Straightforward. So we have this formula for torque as NIAB sine theta. And remember, theta is 90 in this case, so sine 90 is 1. So we get maximum torque. Therefore, the formula changes to NIAB. So maximum torque is NIAB. Remember that. And then we have to calculate B, so make B the subject, which makes it Tau max divided by NIA. Maximum torque is 300, and the number of turns is 200. Current is 25, and then we have the area. Area is 20 times 2400 centimeters squared, which is 0.4 meters squared. Okay, 0.4 meters squared. And we get the magnetic field strength is 0.15 Tesla. So here is the Bainbridge mass spectrograph. So this is an instrument that is used to discover isotopes. So we have an arrangement first of what is called a velocity selector. You may remember that the crosses show a magnetic field that is perpendicular to the screen and into it. So there's a magnetic field here, and also there are two parallel plates, one positive, the other negative, which sets up an electric field from positive to negative. So in the same space here, we have a magnetic field into the screen and an electric field from right to left. So the two fields are perpendicular to each other. These are called crossed fields. So you have a magnetic field and an electric field at right angles to each other. So what happens is when charged particles enter through a gap here and reach the space, there will be two forces acting on it. One will be the force due to the magnetic field, the other will be the force due to the electric field. And if these two forces become equal and opposite, then they cancel out, and there will be no force acting on the particle. And then the particle will be able to go through straight, undeflected. But if the two forces are not equal, then it would be swayed or deflected either to the left or to the right, and they will not be able to pass out through that tiny slit. Now, this arrangement is called a velocity selector because, as we're going to see, it's only a certain velocity that the particles have which will be allowed to go through. So, only particles that have a particular velocity will go through undeflected. All other velocities will be eliminated. All right. What's the formula for the magnetic force? It's QVB. What is the formula for the electric force on a charged particle? It's Q times E. So I have put these two equal to each other. QE is the electric force, QVB is the magnetic force. So we're considering that all these particles have the same charge Q. Okay? And now we can see that the Q will cancel out, and when you rearrange, you get the velocity as E by B. So it's only those particles that have a velocity given by this ratio that will go through. And once these particles go through, they enter another magnetic field, which is B naught here. It's a larger area. And once again, the magnetic field is into the screen. And remember that now the particles will be compelled to go in a circular path, or kind of half a circle here, because you have a particle detector here that will detect those particles that make a certain radius. See, so this particle detector can be moved linearly here. So if you have the particle detector here, it detects particles that go through a smaller radius. But when it's here, it detects particles that have a bigger radius. And we're going to see that the radius is determined by the mass of the particles. Okay? The radius is given by mv by qb, where m is the mass. So the bigger the mass, the bigger the radius, as you can see. And so the particles that have different masses will have different radius, and that's how we are able to find the isotopes of that material. You rearrange to get Q by M as V by BR, and then we can substitute for the velocity as E by B. This velocity is E by B, so the radius is given by E by B, B naught R, which means that the charge by mass ratio depends on the radius. Smaller the radius, bigger the charge by mass ratio. So this is how a spectrograph is used to isolate isotopes. So here is a problem coming up. All right. What is the velocity of a beam of electrons that goes undeflected when passing through perpendicular electric and magnetic fields of magnitude 8.8 times 10 to the 3 volt per meter, that's the electric field, and 7.5 times 10 to the negative 3 Tesla, that's the magnetic field. So what's the velocity? And then what is the radius of the electron orbit if the electric field is turned off? So in this case, the electric field is turned off. That means you only have a magnetic field, and then it'll go around in a circular path. We're asked to find the radius. So the first thing to find the velocity, you set the electric force equal to the magnetic force as we did before. QE is equal to QVB, and then velocity is given by E by B. So what we got to do is just take the ratio of the electric field to the magnetic field. And that will give us the velocity of those particles that will go through undeflected. In this case, it turns out to be 1.173 times 10 to the 6 meter per second, approximately 1.2 times 10 to the 6 meter per second. And so once we have the velocity, if we turn off the electric field, then you only have that magnetic field, we can find the radius using the formula R is equal to mv by qb, which I'm trying to bring out using centripetal force is equal to this. Remember, we did that before. So the radius is mv by qb. Mass of the electron is 9.11 times 10 to the negative 31. Velocity we just got, that's 1.173 times 10 to the 6. The charge of the electron, and then the magnetic field is 7.5 times 10 to the negative 5. I mean negative 3. When we make those calculations, we get 8.9 times 10 to the negative 4 meter as the radius of the electron orbit. Now we have a cyclotron here. A cyclotron is a particle accelerator. So it's basically made up of two hemispheres that look like the capital D. As you can see, there is a D here and there is a D, inverted D here. It's actually hollow inside, and at the center you have a source of charged particles. So that, and then the two Ds are given a high frequency alternating source. So because it's alternating, D1 becomes positive and D2 is negative initially, and the next half cycle D1 becomes negative, D2 becomes positive. So they keep interchanging, becoming positive and negative. So that means when this particle comes out, imagine it's a positively charged particle, it'll be first attracted towards the D that's negative, and then and also I forgot to mention there is a magnetic field in the same region, and you can see by those arrows here the magnetic field is perpendicular to the electric field. So what happens is, because of the magnetic field, the particles make a semicircle. So D1, let's say, is negative, and this positive particle is accelerated through to D1. It's pulled to D1, but it won't go straight. It'll make a circular path because of the magnetic field. And by the time it comes out here, D2 becomes negative. So now it's accelerated to D2. And then by the time it comes out again here, D1 again becomes negative. So it's accelerated into D1. So because D1 and D2 keep becoming positive and negative alternatively, the particle keeps moving, and each time it's accelerated by the electric field, its velocity increases. Therefore, the radius of its path becomes bigger. Remember, the radius of the path depends on the velocity, mv by qb. So as the velocity increases, the radius increases. And finally, you have the fast moving electron, the charged particle beam coming out. And then that can be used to produce fission in a nucleus or whatever purpose. So that's why this is called a particle accelerator. It speeds up the charged particle slowly but surely, and then finally it comes out with a huge velocity and a huge kinetic energy. Let's get the formulas. The radius of the path is mv by qb. We know that. And so we also know that the time period is 2 pi m by qb. And the maximum velocity would be qbr. I'm just rearranging this to make velocity the subject, becomes qbr by m. That means the maximum velocity is determined by the radius, the maximum radius. So if you can have a bigger d, or you can have a maximum velocity. And once we know the velocity, we can figure out the kinetic energy. Kinetic energy is 1/2 times mass times square of the velocity. Okay? And substitute the value of maximum velocity. You get this formula, q squared b squared r squared by 2m, to be the maximum kinetic energy. Let's work out a problem. And before that, remember, frequency is 1 by t. So frequency is qb by 2m, 2 pi m. It's actually called the cyclotron frequency, qb by 2 pi m. So here is the problem. Wow. Okay. Well, I'll let you see it. If the radius of a cyclotron is 0.5 meter and the magnetic field strength is 0.6 Tesla, what will be the maximum kinetic energy of accelerated protons in mega electron volt? Okay, we know that the maximum kinetic energy happens at the last orbit or at the outside of the cyclotron. And this is the formula for maximum kinetic energy. We have the charge of the electron. Oh, it's a proton, but remember, protons and electrons are the same charge. So that's charge squared, strength of the magnetic field squared, radius squared by 2 times mass of a proton. That's the mass of a proton. That comes out to be 6.898 times 10 to the negative 13 joules. But the answer is to be in mega electron volts. 1 electron volt is 1.6 times 10 to the negative 19 joules. Okay? So we're going to change now from joules into mega electron volts. So we'll take this number, and then we know that 1 electron volt is 1.6 times 10 to the negative 19 joules. And then 1 mega electron volt is 10 to the 6 electron volts. So that's how we get 4.3 mega electron volts as the maximum kinetic energy. Well, there's been a lot of stuff that I've explained in this chapter, and I hope it all makes sense. You may want to look at it again. Also remember, there is another problem set on this chapter where I have worked out 10 problems, 10 different problems that combined with these problems, and the lecture here should make a lot more sense and should help you understand this topic. Thank you. See you on the next video.